Welcome back. Problem 11.32. So statement is assuming that prismatic beam AB has a rectangular cross section. Show that for the given loading, the maximum value of strain energy density in beam is equal to umax is equal to 1.15 into U divided by B. So beam is prismatic. Beam has a rectangular cross section. So you have to take the rectangular cross section with width A, with width is equal to B and height is equal to D. I will write it. We have to find this where U max is the maximum value of strain energy density. This U is strain energy of the beam and this V is the volume of the beam. So let's start with the solution. As we are given that beam is in rectangular cross section, so we will write, first draw this rectangular, let this width is equal to B and this height is equal to D, and this will be the this is D, and this is the rectangular cross section of the beam. So our first step is to find the strain energy of the beam. For that we will cut the beam anywhere from this point B and let this distance is B. We will draw the free body diagram over here. So if I draw the free body diagram over here, it will be like this. So this is a point B. From B to this distance is, let this distance is V. So if you cut the beam, there will be a shear force, clear, and there will be a moment. So I will write the shear force as V and there will be external moment M. And you can see that we have a distributed load also equal to W, that is over this portion. This is W. Okay, so we will find, let this point is point K, clear. So we will find the moment equation, that sum of all moment about point K is equal to 0, taking the counterclockwise moment as positive. Now moment about point K is due to this W load, and this W load when converted into point load, it will be W into V, and it will be acting at a distance of V by 2 and creating clockwise movement. So it will be negative. So I will write it minus W into V. This will be a point load and it will be acting at a distance of V by 2 minus this moment which is clockwise. Their sum must be equal to 0. So from here you will get moment is equal to minus 1 over 2 W V square. Now this is the moment equation for the beam. So its strain energy, total strain energy will be integral of 0 to L, because it's for, here we can see X, not X, that is V. Okay, sensor is not working properly. Okay, so you can see that this V is greater or equal to 0 and less or equal to L. So M square into dx over 2EI. Okay, so you can put the value 0 to L. M square is minus 1 over 2 WV square, and we will take the whole square, divided by 2 into EI multiply by dx. So when you solve this, it will be equal to W square over 8EI into integral of 0 to L, and we will left with V square into dV. This is again, this is also dV. Okay, so total strain energy will be equal to W square into W square over 8EI 8 EI. This is V4 because this is V square, this is V4. So make a correction, this is V4. W square over 8 EI, and if you integrate it will be V5 over 5, and the limit will be 0 to L. And if you further simplify it, it will be equal to W square L5 after putting the limit over 40 EI. Now this is the total strain energy of the beam for the given loading. Okay, now we know that moment is given as -1 over 2 WV square, and for maximum moment V will be equal to L. So maximum moment modulus will be equal to 1 over 2 WL square. Okay, from this maximum moment we can calculate the maximum bending moment, and maximum bending moment is equal to maximum bending stress is equal to maximum bending moment into C divided by I, and you will get this maximum bending stress is equal to maximum moment into C divided by I. Now we know that strain energy density Umax is equal to sigma max square over 2E. So you can just put the value, it will be maximum bending moment square into C square divided by 2E. Clear? 2E, where maximum bending moment is M square C square, and there will be I square as well, because we have, this is the formula, so this is I square. Okay, so you can put the value of maximum bending moment. So maximum bending moment is 1 over 2 WL square, so it's square into C square divided by 2EI square. So upon simplification you will get it W square L4 C square over 8EI square. So Umax, which is maximum strain energy density, is equal to W square L4 C square over 8EI square. So this is our strain energy density. So let this strain energy is equation 1 and this is equation 2. So if divide 1 by 2, so you will get U over U max is equal to, U is W square L5 over 40 EI, W square L5 over 40 EI, and divide by, it is W square L4 over, there is C square over 8 EI square. Okay, now when you solve this you will get Li over 5C square. Okay, now we know that for rectangular beam I is equal to, here this is B 1 over 12 BD square, BD cube, sorry, that is B 1 over 12 BD cube. So I will put the value L into 1 over 12 BD cube divided by 5 into C is, C will be, if this is the neutral axis, so C will be equal to D by 2. Clear? So we will put the value of C is D by 2 whole square. So D by 2 whole square. So upon simplification, you will get U over U max is equal to 1 over 15 LBT. So if this is the rectangular cross section, this is B, this is D, and this is the length L. This is length L. So volume, that will LBD is equal to volume, so it will be equal to 1 over 15 into D. Now we have this equation, U or U max is equal to V by 15. So again we have been asked to find U max. So U max is equal to 15 multiplied by U, capital U, divided by V, which is the proof that strain in maximum strain energy density is equal to 15 multiplied by total strain energy divided by the volume of the beam. So I hope you have enjoyed this video. Again, if you have any question, you can ask me in comment section. If you have any question, do comment and give your feedback about my videos as well. Thank you for watching.